Hello everybody, thanks for joining. We are ready to start. And during this web meeting, you will learn more about our software for quick and easy pipe stress analysis. We are going to provide you with live demonstration of START-PROF and tell you a little bit more about its advantages. And besides, those of you who will stay with us till the end of the webinar. And with this, I'm handing over the presenter's rights to Alex Matveyev, who is the head of pipe stress analysis software development sector. Alex.
Hello, everyone. Thank you that you attend our webinar. I will tell you about pipe stress analysis software, START-PROF. Our main goal is to develop the easy and fast software, easy to learn software. Here you can see the list of main users of our software. We have about 3,000 companies who use our software, and it has a long history of development, more than 50 years. The first version was created in 1965 year. It was rewritten to different machines, mainframe, DOS, and then Windows. And we have implemented all the most frequently used codes for pipe stress analysis. It's ASME codes, European codes, Russian codes, and Chinese codes. And the code for fiberglass piping analysis. Some people ask us a question. If your software has so many users and has so long history, why we never heard about it? That's why we translate our software into English language just about 3 years ago. And we enter international market just in the past year. So we have powerful capabilities of integration with other software, like 3D modeling software, PDMS, Smart 3D, Plant 4D, and other software with stress analysis software like Scissor2, AutoPipe. And START-PROF can read the PCF format files. You can import your model. Now let me show you the live demonstration of the software. Here is the START-PROF. Let's create the simple piping model. Here you can see several codes that we can choose. It's ASME codes, B41.1, B41.3, and other codes. It's Chinese codes, European code, other Chinese code, Russian codes, and fiberglass piping code. I will choose the most frequently used ASME B41.3 code. Here you can see that we have several options for this code. If you select different type of codes, you'll see different options. It's the main feature of START-PROF. You don't see unnecessary options, only the options that is related to the job that you are working for. And now let's check which options we have. It's consider the T-branch flexibility, liberal stress allowable, should it be used or not, how to calculate the stress range. Also, START-PROF can use B31J, stress intensification and K factors. It's very easy to use. You don't need to use any site software. You just select this option, and START will model all the T's and all reducers according to requirements of B31J. Everything is done automatically. You can just check this option or uncheck it. Very easy. And several other options. Here you can set the installation temperature. Let it be 31 degrees. Here you can select the test temperature. Let's click OK. Now we create our first model. Let's create the first pipe. We have rigid element and pipe element. Let's add rigid pipe element and specify the properties of this pipe. For example, it will be 32 meters long. The diameter and wall thickness you can specify manually, or you can take it from database. Let me select the pipe shadow 40, this pipe. I click OK, and you can see the diameter and wall thickness fields are now filled. You can see mill tolerance, corrosion allowance, the material, pressure, temperature, test pressure, insulation weight. You can take the insulation weight from database, or you can specify the density of fluid and click OK. Now we have our first pipe. I will add the anchor on one end of the pipe and anchor on other end of the pipe. Then I add the node in the middle and add expansion loop 2 by 2 meters at this point. Here is the expansion loop. Now we can add the bands here. We have several types of bands. It's common bands, meter band, meter joint. It's 2 pipes connected without using the band. Non-standard band, where you can specify the SIF factor and flexibility factor. And long radius bands that is used for main pipelines. The radius of these bands is about 100 diameter and greater. I will select the common band, the long radius. Also, you can select 1 flange, 2 flanges, or no flanges. If you change this option, the SIF factor and flexibility factor will be different. I will choose no flanges. Now we can copy this band to clipboard and paste it in other nodes, just using Ctrl+C, Ctrl+V. Now I can save my model. And our model is ready to run analysis. I run analysis. And let's check the deformed shape of our model. You can see that pipe is falling down because we don't have any supports, and stresses did not pass the strength requirements of the code, of B31 free code. We can check the pipe stress table. Here you can see stresses in main operational mode and in test mode. Here is the stresses: alternative sustained stress, standard sustained stress, allowable stress. This is expansion stress and allowable expansion stress according to B31 free code. all load cases was created automatically. A little bit later, I will show you how this is done. And now you can check any value in this table. Just move your mouse over any cell in this table, and you will see the text that describe how did this value was calculated. Here is the diameter, wall thickness, the moments, bending moment, area, stress intensification factors, bending stress, axial stress, torsion stress, and equivalent stress, and the result value. So you can see it for every cell. For example, this is expansion stress, this is allowable expansion stress. So you can check all values and understand why the stress is so high. Now, if you don't like the units in this model, you can change units at any moment of time. Just click File, Customize Units. And for example, you can select MPa. Now all stresses are in MPa, or you can select KSI units. Now you can see all stresses in KSI units. The same way you can change units for pipe length. For example, this is 15 meters. You can change units to feet. Now you can see that the length of this pipe in feet. And if you will open the properties of this pipe, you can see that lengths are in feet. You can also change the units for diameter, wall thickness, and all other parameters. The units can be changed on the fly at any moment of time. I will return back to the units to see unit system that I used for, and let's check the loads, support loads in this model. You can see the anchor loads in operational mode, test mode, in global axis, local axis, and pipe local axis. Now let's add the supports to this model. I will add the node near the band and add sliding support, V-stop support, vertical stop support with friction factor 0.3. And when I can split this pipe every 2 meters and add in each node the sliding support. Now we have several sliding supports, and we can do the same on the other end. Add sliding support and split this pipe. Now our model should pass the strength requirements. Let's see the results. This is the deformed shape of our piping system. Let's check the stresses. Everything is okay. Now we can check the stress table. We don't see any red cells in this stress table. It means that our model is perfect and all stress requirements are met. Now, let me show you how to define the allowable loads. For example, I can set the allowable loads for this anchor. I open its properties and check this option, check allowable loads, and set some allowable loads. For example, 1 kilogram for each direction. And for example, I can set allowable load for this this support. I set very low allowable loads. Now I run analysis, and here in the error and messages window, you can see errors that load on the support is greater than allowable. When you click on this message, START-PROF show you the exact node where you have a problem. Now let's check the restraint load table and use global axis. Now you can see here the loads that is greater than allowable. So it's very easy to check allowable loads in START-PROF. Now let me show you how to select springs. I will remove allowable loads. Now let me change the projections of this pipe. I will make vertical pipe, and I will add the node here and add here the spring support. For spring support, you can specify friction factor to take into account the friction in this support. Also, I will delete this sliding support and add here the spring hanger. For spring hanger, you can select the rod length, for example, 3 meters. And now I will open the project settings, open additional settings, and select here the code for spring selection. We have several codes, but can be several manufacturers of the spring hangers and spring supports. For example, I can choose Witzenmann, and the same manufacturer for constant load spring selection, constant effort springs. Now I click OK, run analysis, and in output menu you can find the spring hanger and support table. Here you can see the springs that START-PROF has selected, these springs. The same way START-PROF can select the constant effort springs. I can delete this spring and add constant support and constant hanger, and run analysis. And in output menu, I can find constant effort hanger and support output. And here you can see the constant effort springs that was selected by START-PROF. Now let me show you how to define several operational modes for this model. Let me undo the changes. Okay. How to define the several operational modes. I open the operational mode editor, select the first row, and click Add Operational Mode, and copy current values. So all the values was copied into second operational mode. I can call it, for example, emergency. Emergency mode. I will not calculate installation state, and spring hangers will be selected for first operational mode. Now I click OK, and here in this menu you can select the current operational mode, the mode with which you are working right now. I will select emergency mode. Now, if I open pipe properties, I can see pressure and temperature for emergency mode. And I can change it. But I need to change it for all the models. So I select all using Ctrl A, select all, and then just change the properties in the left window. I will change pressure to 20 and temperature to 200. Now, if I will open pipe properties, you can see here the pressure values in 3 different operational modes. It's first mode, emergency mode, and test mode. The same with temperatures. We can see different temperatures here. And also you can select different insulation weight in different operational modes. And you can set different density of the fluid inside the pipe for different operational modes. And also you can set several other properties different in several operational modes. Now I run analysis, and immediately we can see results. This is the emergency mode deformed shape, and this is main operational mode deformed shape. You can see the deformations is different. This is test mode. This is emergency, and this is operational mode. Also, if you open the stress table, you can select operational mode, emergency mode, and test mode. And you can select restraint loads for test mode, emergency, operational, or maximum from all operational modes. Now let me show you how to add the snow, ice, wind, and seismic loads. I open the project settings, and in seismic properties, I select user-defined acceleration. For example, 1g by x direction, 1g by y direction, and 0.7g by vertical direction, and stresses will be checked like occasional. And let's set the wind, snow, and ice loads. I select snow load. We have several codes that can be used for snow loads. I will select the code of the United States. Here we can set the snow load value, for example, 10 kilograms per square centimeter. It's very big load. Ice load, for example, 7 millimeters, the thickness of the ice. And wind loads. In wind loads, we have a lot of codes. It's Mexico code, Colombia code, Canada, China, Russia, United States, and several international codes. I will select United States code, set the wind speed for the first direction plus x direction, and set the stress check like occasional. Now I add another direction, minus x. I can change any values here for second direction, but I will not do it right now. We select plus y direction and minus y direction. Actually, you can add as much directions as you want. You can you can add the wind at the angle 45 degrees, for example, to the pipe, and other directions. So you can define the wind rows for piping system. And now I click OK. Now we need to tell Start how to analyze these loads, in which operational modes. Now you can select here the first operational mode. Some people ask me, they usually ask me, where is the load cases in START-PROF? Why we have only 3 load cases? This is the mistake. It's not 3 load cases. If you select, for example, the first row and click here, you can see that 6 load cases are hidden in first row. It's hanger selection 2 load cases, sustained loads, alternative sustained loads as required by B31 free code, the operational load case, and expansion stress check load case. So we have 6 load cases in first row. Now let me show you. I will add snow and ice loads and click here again. Now you see that we have 12 load cases. The load cases for snow and ice loads was created automatically. Here is the snow loads, and here is the ice loads here. Now we can add wind loads. Click here, and you can see that we have much more load cases, 27 load cases. Here is the wind load cases. And if I will check seismic loads, we will have 48 load cases. And this is only at the first row of this operational mode editor. If you will select the second row, we will have 4 load cases here. If I will check wind loads, you will have 19 load cases for the second row. What does it mean? It means that what will happen if wind will blow in main operational mode, or what will happen if wind will blow during emergency mode with different temperature and different pressure. Now I click OK, and now we should set the wind shape factor and snow shape factor and ice shape factor. For example, snow shape factor is usually 0.4, ice shape factor is 1, and wind shape factor can be calculated automatically, or you can set it here manually. For example, it will be 1.2. But I need to set the shape factors for all my piping systems. So I will just select all, and inside menu, I will add all shape factors: snow load, ice, and wind. And now if I'll open any pipe, you can see that shape factors are changed here. Now I can run analysis. And let's see the deformed shape animation. How does it work? This is operational mode. This is operational mode with snow. I set very big snow load, so the deformations is very big. This is ice loads in main operational mode, wind in main operational mode by X direction, minus X, plus Y, and minus Y, and wind at 45 degrees, and wind and emergency mode. This is emergency mode, wind plus X, and other, and test mode. In operational mode editor, you also can add the friction multiplier. For example, if you will set 0, We usually use 0 value if we calculate for wind loads, because friction stop pipe from moving. So it will give us safety margin. Or you can use 0.5 friction factor. But I will use the value 1 in my model. It's more easy to understand, but you can set any value here. And also, if you want to add, for example, relief valve or any other relief valve thrust force or any other additional forces to the model, for example, forces caused by water hammer, slug flow, or blow, or any other loads, you can just open operational mode editor, select the main operational mode, click add, and add, for example, additional force loads here. I will call it relief valve 1 opens. And now I will add one more additional loads and call it relief valve 2 opens. It's very easy to use operational mode editor because you don't have to create load combinations manually. All load combinations are created automatically by START-PROF. Now I click OK. Then I select the current mode, relief valve 1 opens. Select this node and add additional force, for example, 1,000 kilograms in Z direction. And for example, I can delete the support somewhere and add relief valve 2 additional load. And now we can run analysis. Now I will select the emergency mode. This is deformed shape in emergency mode. And this is relief valve 1 opens. Here you can see the effect of the force that is applied in Z direction at this point. And if you will change to the current mode to relief valve 2 opens, the additional force is applied here at this point. So this is how does operational mode editor works in START-PROF. There are a lot of other features, but we don't have a time to show you everything in this presentation. Now let me show you how to add the flange leakage check. Let me undo some changes. Okay, now I will add the node here and add here the flange pair. This is flange pair here. You have several pipe elements, bands, tees, reducers, concentric, eccentric, valve, cap, valve, joint, and flange pair. I will select flange pair. Here you can specify the length and weight of the flange. And you can set to check the flange leakage. Select the method for flange leakage check. It can be equivalent pressure, code case, DNV, or nuclear code. I will select equivalent pressure. Then you select the flange type. It's Russian Ghost code, European code, or ASME code. I will select ASME. Select the effective gasket diameter. the class of the flange and material group. Click OK. Here we have the flange pair. Now I will add the valve somewhere, for example, at this point. I will add valve. Length will be 400 millimeters. And we will have two flanges on the ends of this valve. I will set ASME flanges, class 300 and material 1.1. Now let's run analysis. Sorry, let me uncheck the wind, snow, ice and other loads because I undo the wind shape factors. Okay, I will set wind shape factors again and run analysis. Now let me check how does it work. Yes, everything is fine. And now let's check the flange leakage. I open output menu and select the flange leakage. Here you can see the result of analysis. It can be shown in operational mode, emergency mode, test mode, and the maximum from all modes. Here is the 3 flanges, 2 for the valve and 1 independent flange. The pipe outside diameter, temperature, axial force acting on this flange, the bending moment, the operating pressure in the pipe, and equivalent pressure for this flange and allowable pressure for this flange. As you can see, the calculated pressure is lower than allowable, so everything is fine in our model, no problem. If the flange equivalent pressure is greater than allowable, you will see red cells here, and you will see the warning messages in this window, error and warning messages. So you have a problem with flanges somewhere. Now, let me show you how to add the expansion joints. For example, I can add lateral expansion joint at this point. This is lateral expansion joint. It's simple joint model. You can specify the flexibility and allowable lateral movement, or you can check, you can take this expansion joint from database. And now we can run analysis. Let's see how does our model works. Our expansion joint works fine. And now I select output and expansion joint deformations table. Here you can see the shear deformation of this expansion joint and allowable deformation. If shear deformation will be greater than allowable, you will see a warning message in error and message window here. So your main goal is to create your piping model and remove all warnings and all errors from this window. If you will not see any errors, it means that your model is perfect. Let me add axial expansion joint here. I will take it from database. For example, this expansion joint, run analysis. And now we can see that we have a lot of problems. The deformations of expansion joint, of this expansion joint, is greater than allowable. We see that stress check doesn't satisfy code requirements. Let's see why it happens. I run the animation and we can see that our expansion joint is stretched, it's not compressed. Why it happens? Because START-PROF apply the great pressure thrust forces. Pressure multiplied by effective area of this expansion joint. And this force is so high that it can break all our piping models. So this is wrong model. The axial expansion joint can't be used like this. It should be placed only in the straight pipe without any turns, without bends, and so on. And let's check expansion joint deformations. You can see here that axial deformation is greater than allowable. So this model is very bad. We should not put axial expansion joint here. Let me delete this expansion joint. Now let me show you how to calculate piping, high temperature piping with creep effect. I will select all my model and change the operation temperature to 400 degrees. It's high temperature and it's greater than creep limit. So a creep effect will happen on this piping. How to consider this? I open operation mode editor and select high temperature for first operation mode. After that, if I will open the pipe properties, I will see the special creep diminish factor and creep self-springing factors. You can take it from database, just click this button and both factors will be filled. Or I will just select the whole model and click here and set self-springing factor and creep diminish factor. Now all the information is applied to our model. We can run analysis and see the stress report for operational mode. Here you can see the special checkbox, creep stress. If I click on it, we will see additional stresses. This stress is calculated according to ASME B41 free code, and this stress is additional by START-PROF authors. It is taken from old Russian code, and that is used more than 50 years. And we can calculate stresses in operational state and, most important, in cold state. The main problem in high temperature piping system is the stresses and support loads in cold state, not in the operational state. In operational state, our piping system feels very good. It's relaxed, it's very flexible, but in cold state, after cooling down, we will have the self-cold springing effect caused by creep. So the most high stresses and most high support loads are happening in cold state for high temperature piping due to creep self-springing effect. I will show you what does it mean. Here is our piping model. Imagine that we heat up this model above the creep limit. If you will apply the weight to this pipe, and strain will rise upon the time. This is time and this is strain. Strain will rise upon the time. But expansion stress will reduce upon the time. Here is the stress at the first heating up, and upon the time it will be lower, lower, and lower. Because of relaxation effect, creep relaxation. So temperature, so the temperature expansion stresses are reducing upon the time, but this causes the cold spring effect. Here is the temperature, stress. When we heat up our piping, the stress is rising. After that, the stresses is falling down due to creep relaxation effect. And after we decide to cool down our piping system, the stress goes to negative area of this graph, and you will see negative stress, and you will see negative support loads in cold state. This effect is called self-cold springing due to creep effect for high temperature piping. So let's check the restraint loads in this operational state. This is loads in operational mode, and this is loads after relaxation, after cooling down. In some cases, the stress can be much greater than stresses in operational mode. So it is very important to check loads and stresses in cold state for high temperature piping. Now, let me show you how to model the vessels. You can model vessel using simple anchor, but you must add the movements of this anchor due to vessel temperature expansion. But you also can consider the flexibility of the vessel. For example, I will show you the special option in START-PROF that can calculate the flexibility factors according to WRC code. WRC. And I will specify the nozzle properties, vessel properties, temperature, length, and material. I should choose another code. It doesn't matter. Now we have flexibility factors. We can copy it, then move back to our piping system and paste it here. This is flexibilities of the vessel. But we can calculate flexibilities more accurate using the PAS Nozzle FEM software. Sorry. Okay, here is Nozzle FEM software. In next version of START-PROF, we will merge two software in one. It will be one software. Finite element analysis of nozzles and tees and piping system analysis. In current version, it's two different software. Let's select the model of the vessel. We have cylindrical shell, diameter, wall thickness, and other properties. You can change it. And properties of the nozzle, diameter, wall thickness, and so on. Material, you can choose material from database. We have a very, we have a great database with ASME codes, ASME code materials, Russian code materials, Chinese code materials, and European standards. Very big database. You can choose the type of the nozzle like this. You can choose the type of reinforcement of the nozzle. I will just show you several options here. I will choose the most simple option. And now we can just run analysis. This is finite element analysis of this nozzle. This is matrix. Analysis is done. Now you can see the stress calculation by by finite element method. You can see the model of this nozzle in 3D. You can see the deformed shape. You can see the stresses, total stresses, tensile membrane stresses, and other type of stresses. And this report show you if the strength conditions are satisfied or not. You can see flexibilities of this nozzle, this table of flexibilities, stress intensification factors, and strength calculation by simple WRC code. It has several restrictions and not so good as finite element method, but we also have WRC code here. And you can copy the flexibilities into the START-PROF model and then check the stresses using finite element method in Nozzle FEM software. In next version, we will merge two software and it will be done automatically. Also, we have the special T. Let me show you. I will add the pipe here. And at this point, I can add several types of T. It's welding T, fabricated T, and other type of T's. And also we have non-standard T. For non-standard T, you can specify the header stress intensification factors, header flexibility factors, and branch stress intensification factors and flexibility factors. The actual model of the T will looks like this. So START-PROF have a complex model of T. It's not just two pipes that connected to each other, or sorry, three pipes. It's more complex model. START-PROF automatically add the flexibilities of the header, flexibilities of the branch, and calculate, add here the rigid element and calculate stress intensification factors in needed cross sections. So it's a very complex model, but everything is hidden inside this T. Also, if you will check here in project settings, the ASME B31J, then K factors and stress intensification factors for all standard T's will be calculated according to B31J automatically. But if you want to calculate it by finite element method, you can open Nozzle FEM software, choose the T model, set the parameters, run analysis, and software will calculate you the stress intensification factors for header, for branch, and flexibility factors. Everything is done automatically. Here is the flexibilities for header, for branch, and stress intensification factors for header and branch. And you have to set these values in START-PROF non-standard T here. In next version, the finite element analysis will be done exactly in, from this dialog box. The Nozzle FEM software will be embedded into START-PROF. It will be much more easy than now. And also let me show you the possible, I will create new model. And I will show the possible types of vessels. Vertical vessel, horizontal vessel, storage tank, the T, conical shell, conical reducer, conical head, elliptical head, hemispherical head, flat head, conical head, and rectangular plate, like this. So you can add any type of nozzle inside this, for example, rectangular plate. So the abilities of this software is very wide. Now, I will show you several models of the vessels. We also can model vessels using the pipe elements. Let me show you. I have several ready models from the START-PROF training, like this. This is horizontal vessel model. We can use transparent mode, and you can see here is the rigid element, the nozzle, and the flexibilities are taken into account here in this junction point between pipe and vessel. This is horizontal vessel model. The same model can be used for a vertical vessel. I can show you another model with column. This is column with reboiler. Column vessel with reboiler. This is how does it works. And we take into account flexibilities of these junction points with nozzles. It's possible in START-PROF. Now let me show you how to create buried piping in START-PROF software. I open our model, but I will change the code to other code that support buried piping analysis. For example, ASME B314. Select OK. Now let me delete this pipe, this nozzle, and let me, I will not change anything here. Now let me add the pipe here. It will be 2 meters long. Then I will add vertical pipe minus 0.5 meters. This is entry point to the underground. Here I will set 1.5 meters underground. Now I select this pipe and set here the pipe is buried option. Now we can see soil tab. Here you can set the depth at this point and depth at this point. Select the type of soil, it's open trench lane or it's trenchless lane, like direct drilling. And we can select the soil type from database. We have database with different soils. For example, I will select the sand and foundation soil below the pipe. It will be large sand. And here you can choose the insulation type. For example, it can be polyurethane foam insulation that is used for district heating networks. And here is the factor of adhesion between the polyethylene casing and the soil. And also we can add the expansion cushions, that is usually placed on the turns of the pipe in district heating networks. START-PROF is widely used for district heating network analysis. We have about 1,000 users who designed district heating networks using START-PROF software. Here we can select the outer casing diameter and wall thickness of casing of polyurethane foam insulation. This is buried piping. And let me add the horizontal pipe by Y direction, 50 meters. This is the soil surface above the pipe, and I will add here the anchor. Now let me copy the bands from here to here and here. And now we can run analysis. Let me change the temperature because the temperature is too high for this code. I will set 100 degrees and run analysis. Oh, sorry. I have another emergency mode that has much greater temperature. I will delete this. And now it should work fine. Okay. Now you can see the soil springs that was placed by START-PROF automatically. You can see the deformed shape of this pipe. Also, you can add the expansion loop here. For example, 2 by 2 meters. Oh, sorry, 2 by 2 meters, 90 degrees, and add bands. And immediately run analysis again. It's very fast and easy. So simple buried piping models can be analyzed by about 30 minutes. And we can see the deformed shape of our piping. Also, we can add the water. The pipe can be underwater, and START-PROF will consider the change of soil properties if it is below the water surface. And we can consider soil movements. For example, landslide or subsidence of the soil below the pipe, or any other effects on the piping system. Everything is possible. And when we calculate district heating networks, START-PROF also calculate the soil weight above the pipe. This is finite element model that is built inside the START to calculate the cross-section deformation of the pipe. And the soil model looks like this. I'm sorry, a moment, where is it? Here. Yes, we have the soil model with 3 springs. The first spring model, polyurethane foam insulation flexibility. Second model, expansion cushion flexibility. And third spring model, the soil flexibility. Also, START-PROF can analyze FRP piping, fiberglass piping. I can just select the ISO code for fiberglass. I select all piping, change the temperature, and change the material, for example, to Weberstone 55. That's all. Now I can just run analysis. Oh, sorry. I will change the material for the bands also. I will change to Weberstone 55 and immediately run analysis. It's very easy. Just 2 clicks of the mouse and you have the FRP piping model analyzed. Here is the stress in FRP model. We have a special database with properties of FRP material. Here you have the envelope for FRP material, qualified stress, elastic modulus in hoop direction and axial direction, and other properties. And also we have material for plastic piping. For example, polyethylene 100, PE, RT, PP, PVC, PVDF piping, and you can see the properties. This is the special factors to build the curve to calculate allowable stress depending on temperature and service life, expansion factor, Poisson ratio, and creep modulus. So we can just open this piping model, select the plastic piping code, plastic piping systems, and select all and change material, for example, to PE 100, and then change material for all bands, PE 100, and immediately run analysis. It's very, very fast and easy. Now we can see stresses in plastic piping. Here is the deformed shape. Plastic piping material is very flexible, so we need to put much more supports for this model. The supports is not enough. Also, START-PROF can import the model from Caesar 2. Here is the Caesar 2 neutral files, CII. I just select one of them and just drag and drop to start. START-PROF opens this file. This is model from Caesar 2, and we can run analysis, save the changes, and run analysis. Let me close it and open again to get the cyclic loads. Now you can run analysis. Sorry, temperature cycles is not set. Okay. Okay. Now the model analysis is done. You can immediately see results. How does it work? The stresses and all other results for this model. And I can show you the bigger model like this. I just drag and drop it here. And you can see this is model from Caesar 2 converted to START-PROF. Also, START-PROF can open PCF files from 3D modeling software. As you can see, all restraints, all the pipe properties, the material, pressure, temperature, and everything else, everything was converted to START-PROF. And also I will show you how to create reports in START-PROF. You can create custom reports, just analyze the piping system and then use File, Export to Microsoft Word. Select which tables you want to see. For example, stresses, you can add another table, for example, displacements and internal forces in operational state and test state and everything else. You can change parameters and just click OK. Select the file name and you will see the results in Microsoft Word after report will be created. Here is the report with all the analysis results. And also you can copy every table to Microsoft Excel. Just select Edit, copy entire table, then open Excel and paste it here. So you have full capabilities to create reports from piping stress analysis. That is almost all that I had to say. Thank you for your attention.